everyone, my name is Jiawei Chen. Today I'm going to talk about our work, Multi-Modal Video Transformer for compressed video action recognition. In this work, we are looking at the supervised video action recognition problem. So the goal is given a video, we want to classify that into one of the action categories. Most of the current state-of-the-art models rely on either 2D or 3D convolutions for spatial-temporal modeling. Despite the success achieved by these convolutional models, we argue that they are not the best way to do video modeling because they are inherently designed for modeling short-range data. On the other hand, some recent works have shown very promising results from applying self-attention mechanism to the vision problems. Compared to convolution, the self-attention operation is much more flexible in a sense that it can capture both long-range and short-range dynamics, and that's why we want to explore this direction. Another fact that makes our method different is that we choose to work on compressed videos instead of decoded videos, because compressed videos have a higher information density and provide free motion information. Now the key question is how we pre-process the different modality data in a compressed video so that we can feed them into transformer models. Inspired by the recent vision transformer works, what we have done is to simply decompose each modality into a sequence of non-overlapping patches. Then we can map every patch into a feature embedding using a linear projection. We also add a positional encoding to each embedding in order to preserve the original spatial temporal location information. Here's a detailed diagram showing the proposed method. In specific, we have developed 4 model architectures shown in the green panel, and the 3 cross-modal attention mechanisms to facilitate learning across modalities. We started from a model that measures pairwise interactions between all input tokens, and the benefit is that we can do full spatial-temporal self-attention across all the modalities, but the disadvantage is that the cost of this scheme is very high. In the second variation, we decompose the joint self-attention into a temporal attention and spatial attention in order to reduce computational cost. In the third version, we move a step forward by factorizing the self-attention over the modality dimension. At each transformer layer, we attend to space, time, and the modality dimension sequentially, and therefore we can further reduce the computational cost. Our last proposed architecture restricts the factorized spatial and temporal attention to non-overlapping local windows, meaning when we compute self-attention for a patch, we now only consider neighboring patches. In this work, we also developed 3 cross-modality attention mechanisms. The first one is called merged attention. Given a query from one modality, it considers all of the keys and values regardless of the modality type. Alternatively, we can also allow queries to interact only with the keys and values from other modalities. We refer this mechanism to co-attention. We also propose a new computation-free method called shift-merge attention. Specifically, we discard the query and the key embeddings and directly work on the value embeddings by first evenly splitting each embedding into 4 portions, and we then shift and mix the embedding portions from different modalities but at the same spatial and low temporal location. Our experimental results show that the third model variation equipped with the merged attention achieves the best trade-off between the classification accuracy and the computational cost. We also show that the iframe is the most critical modality for a task. It is interesting that the audio modality also plays an important role for the recognition task. We then compare our best performing model with SOTA methods on 3 benchmark datasets. Our model manages to outperform previous SOTA results on both UCF-101 and the Kinetic 600. We also set a fairly competitive benchmark for Something-Something-v2. To conclude, we present a pure transformer approach for action recognition in the compressed video domain. Compared to existing approaches, our method does not rely on decoded video frames and thus saving time and energy. It also serves as a strong baseline for the video action recognition task. Thanks.